But if what you're interested in is particles beyond the standard model and you want to go way up to high scales, particularly for the gluon-gluon luminosity, then it's very bad indeed, really. There's quite a lot of uncertainty. So what consequence does this have? Just a couple of examples of the consequence of it. This is a plot from Atlas at 13 TeV of what's called the Drell-Yan production cross-section, which is a term for QQ bar to mu plus mu minus. And there are the data, you can see them. And extrapolated, you can see predictions, well, from the standard model, but also from the idea that there might be a higher mass Z called a Z prime, and you would get a curve like this. So this plot's only going up to 2 TeV, although I must say, you know, if you've lived as long as I have, 2 TeV seems like an amazing energy, but that's about the limit at the moment. And what you can see is, on the bottom plot is the data plotted and the uncertainty of the prediction also plotted in this grey band. So you can see as we get up to higher masses, the uncertainty of our predictions becoming quite large. So if we want to really see where we have something new like the Z prime, well, this is essentially what's getting in our way, right? That we can't necessarily tell the signal from the background. That was in the sector of QQ bar. Let's look at glue-glue, because many of the interesting processes of the LHC are gluon-gluon initiated, say gluon-gluon to gluino-gluino, if one is still thinking about supersymmetry. And we need a very high scale to produce new things like gluinos. Now the gluon-gluon luminosity at high scale, I've blown it up here on a linear scale for high mass. You can see just how badly known it's getting. And that affects then the gluino pair production cross-section according to the scale as being very badly known. And that's the issue. So, however, I said at the beginning that as well as looking at high scale for new things, we can instead measure precisely things we know well. So, unfortunately, the uncertainties on our parton distributions are also limiting observations that we might make by measuring discrepancies from standard model values. So if we think about the W mass, right, the W mass itself is predicted in the standard model in terms of other standard model parameters like the fine structure constant and the weak coupling. And there is an extra term in this that represents the higher order loop diagrams in this calculation. The loop diagrams I've drawn here just have well-known particles in them, like Higgs, Z, W, top, another Higgs diagram. Various loops you can calculate and calculate what this discrepancy should be. Now suppose there are other high-mass particles we haven't discovered yet. They can also be in these loops and they would alter the value of this delta R. And they might very well make it increase. Now, in that case, the value of mass W is going to differ from its standard model value, and that's exactly what seems to have been seen in the latest measurement from the Fermi lab. So this plot is different world measurements of mass W. Here's the Fermi lab measurement here, and there's the prediction from the standard model. It's quoted by CDF to be 7 sigma out. Now, how can that actually be checked, right? We never believed just one experiment. It can, of course, be checked at the LHC. And the most accurate LHC measurement to date is from Atlas, and it's shown on this plot. It's this one here, much more inconsistent with the standard model. But what we have at Atlas is an uncertainty of 19 MeV as opposed to 9 MeV from the CDF measurement. And out of that 19 MeV of uncertainty on the Atlas measurement, approximately 10 MeV of it is coming from the uncertainty on the parton distributions. So we are not in as favoured a position with regard to that at the LHC, because we're using proton-proton, not PP bar. And this means that we're largely colliding not two valence quarks as they are at the LHC, but we're colliding C with C, particularly since our kinematic region is mostly in the C quark region. So we have larger uncertainties due to that, and it's not very clear that we can improve this quickly, but the rest of what I'm going to talk about is how we might be trying to improve it. This is just a second example with regards to the electroweak mixing angle. And what's shown here against, essentially against luminosity, is the way that the error on this is an error of sine squared theta w times 10 to the minus 5. The error will decrease statistically, going down like that. But the PDF error will not change at all unless something's done. And they tried to make an optimistic assessment of how much that might change in future. This is the red. It's not so impressive, really. So unless we have some further constraints we don't already have, things are not going to improve. So how might we hope to improve? So this now, I showed you a kinematic plane earlier. This has now got the measurements on it. So all these measurements here are actually coming from the LHC. It's the lower ones that come from the HERA EP collider and some of the earlier fixed target experiments. What we're doing now at the LHC is adding to our information about parton distributions by trying to use processes that you can calculate reliably at fixed order, which is currently up to the next leading order. We use Drell-Yan data, we use W and Z rapidity spectra, we use jet PT spectra, top anti-top differential cross sections. We use the bosons in conjunction with jets or in conjunction with heavy flavors. And if we stick at least at reasonably low scales, we can hope that this is still predicted by the standard model and we can feed this information into the PDFs. A little caveat in red is simply one has to be slightly careful of putting in everything and kind of fitting away into your initial distribution the new physics you were hoping to see. So there is ongoing work on that as well. Okay, so let's see how much the LHC improves the PDFs. This is a plots that come from the NN PDF fitting group, and it's a comparison of their standard PDF in the green to one without LHC data in the red. And this is done here for U quarks, D quarks, charm quarks, and the gluon. And you can see that, compared to without LHC data, adding LHC data does indeed reduce your uncertainties. It also changes the shape in some respects. So it's not bad, but it's not really the level of improvement that we really need. And the aim now is to try to get to some, I already said on one of the earlier plots that in the middling region things aren't bad. The trouble is now we need it to be better than not bad. Right? We need to really tell if there's a deviation properly. You need order 1% uncertainties on your PDFs, and from this kind of level of improvement you're really not getting it. And that, of course, also is just one group's interpretation of the data. There are other groups doing this who make somewhat different choices, and the difference between the PDFs also adds to the uncertainty. So what I'm showing here is the gluon uncertainties as they were about 7 years ago, 8 years ago now. So this is, say, MMHT 14 done in 2014. In that colour, and MSHT 20 done at the end of 2020 in a similar colour. But basically this is going from older PDFs to modern PDFs, and the difference in the uncertainties is not actually that impressive, unfortunately. Right? You can see it again illustrated here on the gluon luminosity with the older comparison and the newer one. And part of the problem here is that, say, some of the uncertainty bands have reduced, but the spread between the different groups has increased. So the net effect is unfortunately not as good as we need it to be. So a group called the PDF for LHC makes not just comparisons of different PDFs, but an attempt at combination of them statistically. There was a combination done in 2015, and there's been a new one done in 2021, just released. And the difference between the old and the new, the old is, say, these larger orange-coloured curves, and the new is the redder version of it. And you can compare in each type of plot. These are plots of cross-sections, say W minus against W plus, Higgs against W minus, various different comparisons. You can see that there has been an improvement. But it's the kind of improvement that might take that 10 MeV budget of uncertainty on mass W down to 8 MeV. And then if you add it to the rest of the uncertainty, that's going to take your overall 19 MeV, no lower than about 15 at absolute best. So we need something else. There was a recent study of potential improvements at what's called the high luminosity LHC, which will run towards the end of this decade. Taking processes which are now statistics limited and trying to make reasonable assumptions about the luminosity, but also about the possible improvement in experimental uncertainty. They made overall fairly optimistic assumptions about improvement of uncertainty and pessimistic assumptions. And we see here what improvement one might get in future. So the green is what we have pretty much now, and the red is with a pessimistic scenario and the blue with an optimistic scenario. There's actually not so much difference. And we can see that the improvement we might get, well, it's factor of 2 at best, right? So to that I would also add, are we perhaps being a little bit too optimistic? Because any study of future data always does it as if future data are going to be perfect. And data are never perfect. And in particular, one thing we've realized recently is that the reality with the LHC is it depends, when you're trying to get parton distribution information out of it, on many different data sets analyzed by different groups within the collaboration who have somewhat different procedures for the evaluation of systematic uncertainties. And working out what the correlations are between, say, a measurement in W plus jets on your jet energy scale and the measurement in inclusive jets, you really need to be correlating those. Mostly extractions do not correlate. And this is just a plot of the difference between, in the red, putting in the correlations, or in the blue, not putting them in. And it's for the d-valence part, the d-bar and the gluon, where you get the worst discrepancies. What you can see is that you're going to get worse than 1% effects if you don't account for the known experimental correlations. And this has hardly been done at all so far. So ultimately, right, if we need to do better, how can we do better? Well, maybe what we need is new deep elastic scattering machines. So the proposals have been to have an electron recovery linner into the LHC itself. It looks to me now from the, all the news from CERN that this is quite unlikely. So the future is probably with what's called the FCC, the Future Circular Collider, that may run not just in EE mode and finally HH mode, but also in EH. But somewhat earlier than that, we are also going to get the electron-ion collider at Brookhaven. And that one, at least we know now, is going to be built, right? This is the only thing that's currently certain. So, just considering the kinematic reach of these, the first two I mentioned, LHEC and the FCC-EH mode, will, as shown here, they'll reach to lower X. If this is the HERA region, LHEC reaches out to this blue, FCC-EH down to green. That's extending more at smaller X and higher scale. The EIC instead goes the other way. It extends into the high X region, which is also a region where we need improvement. I've just had a few further slides on considering what the LHEC could actually do for us were it to be built. But I won't dwell on that because we now think it probably isn't going to be built. And were it to have been built, then this is a kind of estimate of how much better, say, the gluon or the C could be compared to what they are currently. So, the summary, right? Precision parton distributions are needed to reduce the background in searches for beyond standard model physics, both at the LHC and indeed at any future circular collider HH mode. They're needed for precision measurements of standard model parameters. And it's true that measurements from the high luminosity LHC should improve our current knowledge, but a dedicated deep elastic scattering machine would definitely do better. There are proposals, on the table, but the EIC is the only one that we know is definitely going to happen, so perhaps that's where we need to be looking in future. So, thank you.
Thank you for an excellent talk. Now it's open for questions and discussion. Yeah. First.
Very nice talk, Amanda. I had a question about the uncertainties of the part-order distribution functions that you elaborated very nicely. With regard to CDF, I mean, you said that it's because they collide protons with antiprotons, there's a substantial decrease in the uncertainties there, measurement uncertainties. But what I would like a glimpse of, and it's not possible to do a detailed discussion, is you mentioned that it's a systematic uncertainty rather than statistics. So even if you go to high luminosity LHC, you don't have much improvement. Yes. So maybe a word on that, if you please.
Well, exactly. It is often systematics that are a problem. In fact, the measurements of W and Z rapidity distributions from Atlas are about as accurate as I think you could ever get. They're below the percent level now. They're around the 0.5% level. I don't think you can easily improve on that. So the study that was done for HLHC specifically concentrated on regions which are still statistics dominated. Like if you take the Drell-Yan but you go up to very high energy, then at the moment we're still statistics dominated. And with the various other processes, they were looking in regions where we don't as yet have the data. But you're quite right, we have in fact reached the systematic limit on many of the processes already. I'm sure you must have read the Fermilab thing of the CDF paper, and obviously read it myself and been through all the work they've done on their calibrations, on their systematics. I don't think they could really hope to do better. And we also are looking at every possibility for systematic improvement, but it's not easy.
Thank you.
So thank you for that beautiful talk. I have a comment and a question. The comment has to do with the EIC. The detector design is currently ongoing. There will be very good particle identification, which should help do more than just the gluon, but to disentangle some of the other channels. There will also be good jet capabilities, and I think that will be helpful. Anyone who has a strong feeling as to what is required, what would be useful, this is the perfect time to tell us, and we can be sure that the detector will be able to do that. My question has to do with the information. So you showed us a lot about the longitudinal momentum dependence of the structure functions. How important is knowing the transverse structure?
Oh, I think I caught you were asking about the transverse structure function. Is that right? Yes. I didn't include that at all because, well, for lack of time for some things. But at the moment, the level of information we have on transverse structure functions is roughly akin to what we knew about regular structure functions before HERA. And I think when the EIC comes on, that's when it'll be like the HERA era for TMDs, for the transverse, that we will have so much more information. I'm much looking forward to that. And, with regard to what you said in your comment, there are actually a couple of EIC workshops coming up in June, both of which I'm speaking at, as it so happens, which are dedicated towards trying to glean now what is really needed for the detectors and for the treatment of systematics that would really help in the eventual extractions. Yeah.
Right.
Thanks once again for a very transparent picture. This is a crazy question coming from a sheer outsider. One talks about the quad gluon plasma So does it make any sense, even this macroscopically, by looking at the partons in the collective state of plasmons, which are known in other areas, and get an insight about this structure factor calculation for the electron scattering from the plasmonic groups?
Okay. If I understood you at all, you were talking about the relationship between what the one plasma phase and what we're measuring.
Yeah, and rather than looking at individual momentum distributions of the quarks, the antiquarks, the gluons, view them as a like collective macroscopic wave function state of a plasmon, and then see what happens, and then get some insight.
Okay. The first comment I have is that I didn't try to allude to it very much, but there is a phase when you go down to very low X where you would expect gluon-gluon recombinations rather than merely splitting. You get a very high density region where your equations may need to be nonlinear, and there might be a kind of Bose-Einstein condensating, that it's called a color glass condensate. But I believe that the thing about the difference to the quark-gluon plasma is that the quark-gluon plasma is something that is effectively at high temperatures, which we are not. And so I would have thought the investigations would be better, in fact, done on the data from ALICE, where you're recreating this high temperature situation.
I understand. Thank you.
Okay. No?
From your talk, it looks like that we have to live with this 7 sigma problem for a long time to come. Is that a fair statement?
Sorry, I didn't catch it.
For the W mass.
Yes.
So it's from your talk. Do I go back with this, understanding that we have to live with this 7 sigma difference for a long time?
I think it will be a fair length of time. I mean, obviously our people within Atlas looking at this have been desperate to see what it is they can find that's wrong with it, right? And they have two particular criticisms I won't go into, but it turns out that the effect of the two criticisms almost cancel each other out, so that they can't find a reason for the shift, right? I mean, you can criticize maybe the errors are optimistic, but the shift is very large, and at the moment we don't understand why the central values are so different. And I'm sure there will be more measurements in the next few years, but I think it could be the end of the decade before we really know.
Because if you look at, I think CDF mean value has not changed much from the earlier one.
Yeah, but
it's only the error bar which has come down.
No, also the mean value.
The thing is, the mean value previously had such large errors, but I showed only one plot there, and when you take things like there's a LEP combination, there's a Tevatron combination, and so on, when you take all those, this new measurement does seem to be a bit more anomalous than anything we had before. But, I think what can you say about it being in agreement with previous central values if previously the error on the centivalve was 40 MeV or something? It's yeah.
I had a very quick question about the EIC. The block went too quick. Can the EIC contribute to better define the PDFs in the X-range relevant